Hello everyone. In the previous chapter on 2D elasticity, we had spent a considerable amount of time discussing various problems within the broad paradigms of plane stress and plane strain. So, plane stress and plane strain. And if we quickly recall, this plane stress category of problems, this had to do with very thin kind of structures like plates, which had a certain kind of loading, in plane loading, and there are a number of other conditions also here which had to be satisfied. Similarly, for the plane strain, we had to deal with a certain kind of geometry and a very specific kind of loading. Now, despite these rather restrictive uh, considerations, we found out that uh, both these plane stress and plane strain paradigms, they covered a lot of real engineering structures. All right. So, so if you're interested in solving various problems involving beam-like or plate-like structures, then these two categories are sufficient to address those things. However, you can imagine very easily that there are a number of problems which simply cannot be reduced to these kinds of situations, uh, be it plane stress or plane strain. There are a huge number of problems which can be reduced to these kinds uh, of situations, but there are even more number of problems which simply cannot be reduced to either of this. What then? Well, for that, we are going to discuss our current chapter of three-dimensional elasticity. Now, uh, you can easily also imagine that when we are going to talk about that the more general category of such 3D elasticity problems, then there will be a huge number of different methods which will be used to solve those problems. Okay, many different kinds of methods. Now, out of those methods, the one that we'll choose to discuss within this context of 3D elasticity chapter is a one which will have a natural connection with this 2D elasticity chapter. So basically in 2D elasticity, what we did was we used the Airy stress function approach. We used the Airy stress function approach, and we had done a number of different problems with that. And I'm sure that many of the term projects that you are currently doing is also based on these kinds of Airy stress function approach. So what we want to do in this 3D elasticity chapter is that out of the many different kinds of methods that are available to us, we are going to choose a method which has a direct connection with this Airy stress function approach, and that method is called the method of potentials. Okay, the method of potentials. So what we'll see is that this method of potentials is kind of like the Airy stress function, but not quite. And the ones that we'll be focusing on, so within this method of potentials, there are a number of different ways we can proceed in that method, and the methods, the specific ways that we'll be taking up, the main difference you will find with the Airy stress function approach is that while the Airy stress function directly represented the stresses, the sigma xx, the sigma xy, and the sigma yy, or equivalently the sigma rr, the sigma r theta, and the sigma theta theta, what will happen is that in this method of potentials, we are not going to consider, at least within the scope of our studies in this chapter, we are not going to consider any stress potentials. Although please note that within the context of three-dimensional elasticity and within the specific context of method of potentials, you still very much have stress potentials like the Maxwell-Morera stress potential, but will not take up those. Rather, we'll be taking up the displacement potentials. Okay, some of the displacement potentials. So that is so two main differences with the previous chapter. First of all, that we are going to talk about 3D elasticity, that is beyond the scope of 2D elasticity. Second is that we are going to talk directly in terms of displacements. Okay, so uh, so this is about the method. Okay, so using these methods which have a natural link with the previous chapter, what are the kind of problems that we can think of? Now you may I mean one may easily uh, start thinking that this is rather a weird approach of addressing engineering problems. Like you learn a method and then you go about finding problems which will be solvable by this method. Well, uh, as it so happens that when we learn some of the problems which can be solved by these displacement potentials, we will end up learning about the kind of problems which have been historically important in the development of engineering studies. Okay, so for example, so what are the kinds of problems that can actually be solved? Okay, so in this introductory lecture, I do not want to go to launch immediately into the mathematical technicalities of these displacement potentials. Rather, I want to expose you to the problems which serve as motivating uh, basis for these studies. Okay, so what are the problems? So one of the basic problems which can be solved, and one of the earliest problems also which was solved by these displacement potentials, is uh, is a situation like this. Okay, so what are the kind? So this is the question that we're trying to answer. So what are the kind of problems that can be solved by this? This is what we're trying to answer here. So let's go to the next page and discuss this. So suppose you have an uh, a very large three-dimensional body. Okay, so for all effective purposes, we can think of it like an infinite body. And within this, let's say that there is a point at which we are applying a point loading, a point force like this. Okay, so we have a specific point here, and at this point we are applying a point loading. Question is, or the problem is, that what is the stress field around this point? As simple as that. Now it may sound simple to pose it like this, but the solution to this, and we'll do this, okay, we'll address this problem, we'll take up this problem, you'll see that it is not so straightforward. Okay, we will proceed by the displacement potential and you'll see that it's not so straightforward. Okay, in certain books you will find that it is presented, the solution is presented uh, in a rather simplistic way. Okay, I say simplistic and not simple because what they do is to provide the displacement potential and do not say much about how that displacement potential was arrived at. Now that I think is a is kind of hiding the real challenges which are associated with this kind of a problem. Okay, so we'll try to expose the real truth behind these kinds of solutions as much as possible. Another kind of problem is suppose so you understand this is a three-dimensional body. So we'll consider another three-dimensional situation where instead of this kind of a full three-dimensional space or three-dimensional body, we'll consider it like a half space. Okay, so suppose uh, we have this kind of a situation. Okay, so imagine that this entire three-dimensional space has been cut in half by a plane. So that is the plane that is exposed here, and you end up with okay, so this kind of a situation. Okay, and what you have here is that you consider a point here, somewhere here, and you consider a point loading here, right? And again the question is that in the three-dimensional solid which is present beneath this thing, beneath this plane, what is the state of stress. So all around this. Okay, now some of you may already be reminded of the Flamand problem which we had addressed earlier, where we had a line loading and we could think of it like we were able to reduce this thing to a two-dimensional situation where we were able to look at it from this side. So if you go back and look at that lecture on the Flamand problem, you'll see what I'm talking about. Okay, but this situation is quite different. Okay, although it may seem that this is a simpler kind of loading compared to that line loading, but actually, because of the presence of this just a point loading instead of a line loading, this is a proper three-dimensional problem. Okay, and the solution to this problem is even more involved than this problem. And because of the historical importance of these two problems, uh, and I say historical importance because these are the kinds of problems which turned out to be the stepping stones towards more involved uh, problems, which led to solutions which had a direct relevance and significance for many different kinds of situations in mechanical engineering as well as in civil engineering. Okay, because of this historical importance, these problems are now known by the names um, of the scientists or mathematicians who first solved them. So this problem is the Kelvin's problem. It's a famous problem in elasticity. So this Kelvin is the same Kelvin which you all have studied in your high school physics, uh, and uh, and this problem, this is so let's call this the three-dimensional version of the Flamand problem, and this is actually bearing the name of Boussinesq. So I believe some of you have already come across the name Boussinesq in the context of heat transfer studies. Okay, there is a variant of this Boussinesq problem also. So suppose you have uh, this kind of a situation again where we have this half space. Okay, and instead of this vertical point loading, we have at this point a horizontal loading which is along this plane. Okay, so this is referred to as the Cheruti's problem. Okay, bearing the name of Cheruti. All right, and as I mentioned already, these are the kinds of problems which served as templates or stepping stones towards more involved problems. I mentioned this in the context of our earlier discussions on the Flamand problem, is that these are the kind of problems which actually led to studies, to hardcore studies in an entire different branch uh, or in an entirely separate branch of mechanics called contact mechanics. Okay, and that is just one example. There is an entire field of study in geology and geophysics, where also they have these kinds or the applications of these things. Again, in civil engineering they have applications of these. So these are fairly broad and very significant kind of problems, and these are the kinds of things which we hope to be able to solve through the displacement potential method. Now, because these are so involved, all these problems, each of them are quite involved, uh, we'll see that we'll perhaps only be able to address the Kelvin's problem in full detail. Okay, uh, and we'll see what if we can discuss something in a simplified fashion associated with the Boussinesq and the Cheruti's problem. All right, now before we actually launch into the technical the mathematical technicalities, uh, let's just uh, uh, quickly state uh, what's the overall plan. Okay, I have till now said that in the 2D elasticity chapter we had used the area stress function, and in this 3D elasticity chapter we are going to use the displacement function. So the plan is like this, that here uh, in the displacement potential method, what we are going to do basically, okay, we are going to express the displacement field u vector in terms of some scalar and vector potentials. Actually, this is not something completely alien to you, because back in the kinematics chapter, we had already discussed that suppose you have an irrotational displacement field, then it is possible to express the displacement as u is equal to u vector is equal to grad of some phi. Okay, because when you take the curl of that displacement field, the curl of the grad of phi is identically 0. So these are the kinds of things that we want to discuss here. Furthermore, please note that since we are going to express the displacement field in terms of some scalar or vector potentials, uh, the governing equation associated with the elasticity problems that we're going to address, that will be expressed not in terms of the stress equilibrium equations. Rather, what we'll do is we will express the stress equilibrium equations, which is basically just this equation, okay, which is this equation which you have come across so many times till now, starting from the stress chapter. We are going to express this sigma in terms of the linear elastic isotropic material behavior, which also you're all familiar with by now. So that is basically, if we write it in terms of the index notation, it's this. So we are going to substitute this thing here, and of course we are going to use this. And you have already done this re-representation of the stress equilibrium equations in terms of the displacement fields. So when we do this, and furthermore this, ultimately what you will obtain is a second order differential equation, in terms of the displacement vector, and you have already done this as part of the problem sheet on material behavior. So I advise you to go back and take a look at that equation, because time and again over the next few lectures we are going to utilize that equation. Okay, so back when we were using the eddy stress function, we used directly the stress equilibrium equations, which was this, uh, because this equation, it is directly satisfied by the eddy stress function representations, and we also went on to use the compatibility equations. Now we are going to use this equation represented in terms of the displacement, and the displacements in terms of the potentials. Please note that in this particular approach of this chapter, we are not going to need to separately take the compatibility equations. The reason is simple, is that because you are from the very outset trying to solve for the displacements, Of course, the moment you obtain the displacements, they are going to be compatible. You don't have to worry about the compatibility separately, which was not the case in the previous chapter, because you were trying to solve for the stresses. Okay, and from those stresses you would be able to find out the displacements. So you really had to worry whether your solution would be compatible or not, and you had to embed the compatibility equations uh, with this, or combine the compatibility equations with the stress equilibrium equations. Okay, so we don't have to worry about the compatibility equations this time. So in terms of difficulties of this chapter, you lose some, you gain some, and you'll see the specific details of it starting from the next chapter. All right, thank you very much.